Hello, in this video we're going to look at choosing coordinates when you have a system that's inclined. So generally that happens if you have something on a ramp. So let's make a picture. So let's say we have this ramp and the ramp is inclined by an angle theta from the horizontal. And we'll have some block with mass m sitting on there. Let's say that it's held with a rope. The rope is pulling on it. It might be sliding it up the ramp, it might be lowering it down the ramp, it might be holding it still. All of those cases would be represented with the same picture here. And we'll assume that there's no friction at this point between the block and the ramp. Our task is to find the acceleration of the block. We're going to do this generically. So we'll do all the cases, whether the tension be big enough to drag it up the ramp or low enough to lower it down the ramp or perfectly tuned to hold it in place. They'll all be described the same mathematically. We'll come up with something generic. Okay, so let's draw a free body diagram for the block. The system is going to be the block. Okay? And let's draw the forces that act on this. We have the tension force directed up along the ramp. We're going to have the normal force. Remember, normal means perpendicular, so it has to be perpendicular to the ramp. These two are at 90 degrees from each other then. And then we have weight, which points down. So that's equal to m times g. All right, now we need to pick a coordinate system. So the coordinate system we're going to pick, instead of doing vertical and horizontal, which you could do, but is going to be a lot more work, instead the coordinate system we're going to pick matches the shape of the ramp. So we're going to have x along the ramp and y perpendicular to the ramp. If I sketched in the ramp here, normally you wouldn't draw this in a free body diagram, but it's like so. All right, another reason that we would have picked that coordinate system is the block can't move up or into the ramp. It has to move along the ramp. It has to move along the ramp. So we know that the acceleration has to be either up or down the ramp. And so that lines up with our coordinate system there. Okay, so as we break down our vectors into components, tension's already along the x-axis, so that's easy. Normal forces along the y-axis, that's easy. We'll have to break up gravity into its two components that match our coordinate system. So for that, we're going to have a component perpendicular to the ramp, a component along the ramp, so that makes a right triangle. If our ramp here is at angle theta, theta also shows up in this triangle because it's a similar triangle. Similar means it's got the same angles. And so theta shows up here. Theta is the skinny angle. So it shows up at the top. Now you could prove that to yourself using some trigonometry, or geometry really, that the angle of the ramp is the same as the angle up here at the top. It's good to do that at least once, but that's how it always works out. Okay, so breaking this into components, this component along the y direction is equal to mg times cosine theta, and the component in the x direction is mg times sine theta. So those are the two components. All right, so now we can write down our equations. We'll have an x direction equation and a y direction equation. Now it turns out we don't really need to write down the y direction equation. That doesn't tell us anything about the acceleration because the acceleration isn't in the y direction. Okay, so to meet our goals, we only need to write down the x direction, which tells us that we have tension to the right, or tension in the positive x direction rather, and in the negative x direction we have mg times sine theta. That's equal to, those are all the forces, so that's the net force in the x direction, which is equal to the mass of the block times the acceleration. So to solve for acceleration, we just divide both sides by mass. The acceleration is equal to tension on mass minus little g times sine theta. And as promised, this is nice and generic. This could be a positive number, a negative number, or 0, depending on how strong tension is compared to the mass of the block and depending on what the angle is. All right. So to recap, the key idea here is with a clever choice of coordinate system, meaning we've lined up our coordinates to match as many vectors as possible and to match the direction of the acceleration. All we had to do was write down one equation. Imagine trying to redo this problem with our coordinate system instead picked say, to the right and up. It must work, but boy, would it be kind of ugly, because you're going to have an equation in the right with the acceleration showing up, or a component of it, and a different component of the acceleration vertical. It'd be a mess. You can try it out if you want, and it's not a bad thing to try. It's good practice, but this is a much more efficient way to solve these kinds of problems. All right, see you next time.